morning, everybody. I changed the order of slides. No, not the order. I added a few slides last minute because of the questions that arrived. It's incredibly difficult to know what your speakers before you present. So there is some doubling, but yeah, I've added some 2 slides on the basics. So maybe this might answer some of the questions, I hope. This is the content I plan for the talk. I would like to start with heat and mass transfer in liquid metal batteries. And I'm sorry I was not able to change from cathode to positive and so on. So I'll use these traditional names throughout the talk. Maybe I'm able to improve during time. Layer coupling and thermal convection in the electrolyte and in the anode, and a short digression if we have the time to unpack. Then I would like to spend some minutes on waves, again layer coupling, and some nice features that were found by Garrett, spiral waves. They have nothing to do with liquid metal batteries, but they came from the research on liquid metal batteries, and they look quite nice, so maybe. Then droplets, how they move or how they detach from the anode, and then the last part is a real mysterious thing. So yeah, let's see. It's about capillarity, but I can only show some effects. I cannot explain them. So this is an add-on to what I planned, just basic electrochemistry on liquid metal batteries, the traditional ones. So we have 2 interfaces, the anode electrolyte, the electrolyte cathode interface, and there are this M, say it's lithium. And when it travels, as we heard already a few times, when it travels or when it goes out of the anode, goes into the electrolyte, it has to shed electrons and gets these electrons back at the cathode and alloys with the cathode material. So the cell reaction, oh, no, that's not the cell reaction, that's a mistake. So we have a potential for the upper interface, 1, and the lower interface, 2. And this is how you describe these potentials, the Nernst equation. There is a so-called standard potential that comes from electrochemistry. It's simply tabulated. And since it's both times the lithium ion that interacts with a lithium anode or with a lithium bismuth cathode, this standard potential is the same. To get the cell potential, you subtract the 2 potentials of the interfaces. And because the standard potential is the same, it drops out. And another important information is the activity, sort of a concentration, of a pure metal is by definition 1. So you end up with a very simple equation for the cell potential at rest. There is just a prefactor, including temperature, Faraday constant, and how many electrons are shed by the metal, and the gas constant, and then the natural logarithm of the activity of the alkali metal in the alloy. So this describes you in a relatively simple shape, but it hides a lot of things, of course. It describes you the open circuit, so-called open circuit potential when no current is flowing. Yeah, then these are things we already discussed. I've written this again here for the concrete case of lithium bismuth. This is the system I'll stick to for most of the talk. And the activity, as I said, is just the activity coefficient multiplied by the concentration. So the higher the concentration, the higher the activity, the lower the cell voltage is. And you can see this here in the measurements by Webner and Huggins a few decades ago. So initially, if you have pure lithium versus pure bismuth, the cell voltage is above 1 volt, and rapidly it decays with increasing concentration of bismuth, lithium in the bismuth. And here we have this line in the phase diagram. So here is 0 lithium in the bismuth, here is only lithium, no bismuth. And when at 450 centigrade during discharge, we travel along this line. Here we are passing from completely liquid into partially solid. So we get formation of intermetallic compounds, namely lithium-3 bismuth, and at this stage 75% lithium, 25% bismuth. Everything is this intermetallic compound. That's very high melting, as was mentioned already. So typically we would like to avoid this range of the phase diagram and stick to this one. That means, and yeah, if you have the phase transition as everywhere, the potential remains constant. So these constant lines, they belong to the two-phase region here. When you cycle this lithium bismuth cell, a current is flowing, and current flow means ohmic losses, but there are additional loss mechanisms that might or might not occur. There is activation loss possible at the anode, activation loss possible at the cathode. Activation loss pays for charge transfer through the interface. And then we have concentration, so-called concentration over voltages. And during discharge, they decrease the cell voltage. So the cell voltage during discharge is lower than the open circuit potential. During charge, they increase the cell voltage. So you have to apply a larger potential than the open circuit potential to get the charging current flowing. Happily, activation over potentials are very small, so charge transfer is extremely fast on liquid-liquid interfaces. The only thing typically remaining is concentration over potential in the cathode. And this is a really important point, because the open circuit potential is determined, as I said, by the logarithm of the activity, but the logarithm of the activity, the concentration, at the interface, directly at the interface, where it plays a role. So if you have a higher concentration at the interface compared to the bulk concentration doesn't help you at all. You have to take into account the interface concentration. Therefore, mixing, as was discussed already, is really, really important. So this is an experiment we did with this tiny, tiny cell, where we could look it sits in a glove box filled with argon. So during charge, everything looks quite good. So we have to pay, of course, for ohmic losses, but then, yeah, we simply increase the open circuit potential, and yeah, it's a linear offset, basically. And connected to this, we have a very strong flow here, as was already mentioned. So the thing is, during charge, you start, of course, from discharge state. Discharge state is a very good mixture of lithium and bismuth. We assume it as homogeneous. And out of this homogeneous mixture on the top, you remove the light component. That means the density on top gets much larger than the surrounding density, and more or less immediately solutal convection sets in. And yeah, after 8 seconds or so, it's already in full swing, and it mixes the cathode very nicely, so that the interface concentration is not much different from the bite concentration. Unfortunately, during discharge, the opposite happens. What we do is we're depositing very light lithium, density 0.5 grams per cubic centimeter approximately, into very heavy bismuth, 11 roughly grams per cubic centimeter, and we generate an extremely stable density stratification. So this, we heat the cell from below, so we would have a thermal Rayleigh number, but that would, if it could, generate thermal convection, but this thermal Rayleigh number would only be amount to roughly 30, whereas I'm missing a minus sign here, the Rayleigh number for the solutal, for the stable stratification is much higher, 10 to the 6 roughly. And this results in a diffusion overvoltage that comes from the cathode. This is this gray area. So what we would expect from ohmic losses alone would be this orange line. What we get in the experiment is the blue line, and what we get from the model is the red line. That means the model is quite okay, but we have substantial voltage losses due to this concentration layer, due to the stable stratification. And if you switch off back to open circuit potential, the open circuit potential takes some time to relax, so it has to diffuse away, and then we are back to the open circuit potential that we would expect for the bite concentration. This was discovered quite some time ago, but not discussed in too much depth. Of course, they were interested in getting something running for space applications, but this is, I mean, the phenomenon itself is not very new, but mostly it's assumed that you have to take care of ohmic losses alone, and yeah, concentration over potentials do not play such a huge role. So this is a different cell chemistry. It's potassium and mercury, something that you would probably not anymore build because of health reasons. If you look a bit closer on discharge, and I'm now, the next few slides are all taken from Paolo Personeta's thesis, basically. If you look closer, solutal convection does not immediately sets in, but it needs some time. And Paolo did a very careful numerical study on the set-in and the behavior of solutal convection, and I will just show a few of his results in the next slides. So remember, we are concentrating at the moment on the cathode alone. We do not talk about the rest of the liquid metal battery. This is diffusion during initial diffusion during charge. So the density ratio follows the typical square root function that's typical for diffusion, and this is the concentration in the cell. Yes, numerical results 2D axisymmetric. So we have no flow, no advection. Concentration evolution is purely conductive. But then convection sets in with a deformation of the equiconcentration isolines, and we have small but fast-growing velocities. Plumes develop. These plumes touch the bottom, and then we are almost in a sort of quasi-steady state. Paolo has drawn this nice chart here. Why do we have these remaining fluctuations? So basically, if you have good mixing, there is not a very large density gradient. A small density gradient results in less velocity results in less mixing, results in larger density gradients, results in larger flow. So this is the cycle that produces these long time fluctuations, so to say. Onset time turns out to be determined by inner scaling, so it depends. It does not depend at all on the layer height and the aspect ratio of the cell, but it is a function of the Schmidt number. So diffusion plays a role to determine the onset for solutal Rayleigh convection. This is also known. Paolo also did 3D computations using Zemtech. They are, of course, much more costly than the 2D computations, so he did only a few cases. But basically the same behavior. The plumes start to descend. You get a lot of plumes on the first instability, or on the onset. And then these plumes mix, hit the bottom, they are damped at the bottom. We come to this velocity minimum, and then sort of a stable flow sets in that looks in 3D. So these are equi-density contours, and this is a view from the top on dilithium concentration, basically. It turns out that the Sherwood number that describes mass transfer is proportional to the Rayleigh number to the 0.2 power of 0.2 in the high Rayleigh number regime. There is another regime for very low current densities that I have not discussed and will not discuss. But this scaling that is found for the high Rayleigh number regime fits very well to what was found by Weier, 2020. And we could use the Sherwood number to estimate the concentration polarization that I talked about during charge. Peckley number, that means basically the root mean square velocity, scales with the Rayleigh number to the 2/5. This is as well in agreement to what was found before by Weier. And using the Peckley number, using this relation, we can of course estimate the velocity magnitude during charge. There is often the question, are 2D computations sufficient to derive the scaling we arrived at? And this is a comparison for two different cases. For 3D, this is the solid line and the dotted line, 2D results. And it looks fairly okay. So I guess the scalings should be valid for the range under observation. Yeah. Now coming back to the full cell, to the full problem. This is the purely conductive temperature profile, and I've shown here some material properties. So of course, very good electrical conductivity, very good heat conductivity in both metals, less so in the molten salt. And in the molten salt, therefore, relatively large ohmic heating, and this parabolic conductive temperature profile that we expect. Norbert did computations on this problem using open foam in such a way that he used a parent-child mesh technique. So we have a parent mesh that's for the whole cell, and we compute temperature on the parent mesh, but velocity and pressure and concentration in the cathode only are computed on the child meshes and then mapped back to the parent mesh. And this mapping happens in every iteration. But this way, we can couple thermal and solutal convection for the whole cell and can get some information about what's the most important driving force for convection in the whole cell, in the whole battery, so to say. We would like to look at heat transfer in the fuel cell and mass transport only in the cathode. There is explicit mechanical coupling at the flat interfaces, so the interfaces are assumed to be flat, but we have learned that the velocities are relatively small, so there is no danger of large interface elevations. So this is probably a valid assumption. So then we have continuity of the velocities. There is zero normal velocities at the interfaces, and there is, of course, momentum coupling at the interfaces. And that's important, this mass flux that we discussed, and the mass flux is described by Faraday's first law. It's directly proportional to the current density we apply, the molecular weight of the metal, the Faraday constant, and yeah, how many electrons are given away or taken up. So kinetic energy in these three layers during charge is by far highest in the cathode, where it's driven by soluble convection. It's an order of magnitude less in the electrolyte, and it's even lesser in the anode on top. So this is just a snapshot. It shows high velocities, as I already said, in the cathode, lower ones in the electrolyte, and very low ones in the anode. And if you look at these, at the colors, you see that what we have is viscous coupling, not thermal coupling. So in thermal coupling, we would have the same velocity direction on both sides, normal to the interface on both sides of the interface, but this is obviously not the case. We have the same tangential velocity at the interface. So what we see here is viscous coupling. Coming to thermal convection in the electrolyte and in the anode, there's a classical Rayleigh-Bénard convection. A lot has been written about, where you have cells extending over the whole layer depths. And there is less well investigated internally heated convection that happens in the electrolyte. Of course, many papers have been published on this as well, but it's comparably less investigated to the classical case. So the left one in the anode, the right one in the electrolyte. Critical Rayleigh numbers for some real setups. So to say, we have the anode height here, the current density we could apply, and different electrode thicknesses. And it turns out that for relatively flat anodes that are reasonable, they would be below 20 millimeters or something, because you have typically not too much material in the cathode either. You would not expect a large flow in the anode. The same is true for the electrolyte. If the electrolyte is relatively thin, like 5 millimeters, surprisingly, you wouldn't expect much of a flow. But for a thicker electrolyte of 10 millimeters, the critical Rayleigh number would be exceeded for about 0.5 amps per square centimeter. A few examples for internally heated convection. So it happens in mantle convection, magma chambers, the outer region of stars. Venus atmosphere was under discussion. Severe accidents in nuclear facilities, you might have the core going down to the bottom, heating the vessel, and then you have a mechanical break of the vessel and sprays out the core material. This can happen. So it's internally heated as well because of the decay. And similar flows arise from Rayleigh-Bénard convection with density inversion like normal water around 4 centigrades. And of course, there is the example we are talking about, liquid metal batteries. So this is the electrolyte. And here we have the so-called convective cooling parameter. T star is the maximum temperature for the purely conductive case, and T max is the maximum temperature for the convective case. And I've told you that the 5 millimeter electrolyte is stable all the time, basically, but the convective cooling parameter is above 1. That tells you there is convection. And this convection is shown here, looks very regular. The highest velocities, they appear at the interface of the electrolyte to the cathode. That means the soluble convection during charge mix your electrolyte and gives you much better heat transfer on the lower boundary of the electrolyte compared to the upper boundary layer. For thicker electrolytes, internal convection becomes dominant, and we see this signature of penetrative convection, so basically a stable layer on the lower half and an unstable layer on the upper half, and the location of the maximum velocities switches to the upper half of the electrolyte. Computing Nusselt numbers at the two interfaces tells you the same. So Nusselt numbers at the lower interface for thin electrolyte are higher than at the upper interface, but it switches around. For thicker electrolytes, there it behaves as you would expect, higher Nusselt numbers on the top interface compared to lower Nusselt numbers on the bottom interface. Yeah, I think skip this digression. Electro-vortex flows we talked about as well already. Maybe, yeah, Weier did not discuss this case, but it's interesting. So, of course, what you would like to have from the cell is maximum voltage. So during discharge, you would like to mix. And Weier asked the question, will we ever be able, by applying electro-vortex flows, to fight against this massive stable density stratification? And Weier and colleagues did a relatively long-running simulation, and they found that it looks bright for the first few hundred seconds. So at least there is electro-vortex flow, but it does not really disturb the stable density stratification, and it gets worse and worse with increasing time. So the stable density stratification wins against the electro-vortex flow, so to say, and he came to the conclusion that sufficient mixing is unlikely for moderately sized cells. And this is because you can relate the strength of the electro-vortex flow as well as the strength of the density stratification solely to the current going through the cell. So both are related, and you can make an estimate. Weier did and came to this conclusion. Then Norbert had the idea of adding a vertical magnetic field, inducing swirl, and trying to break this pessimistic outlook that way. And he was successful, as you can see here, at least for the first 5 minutes. There is a dramatic decrease, increase of the cell voltage due to swirling flow that is generated by the cell current and the vertical magnetic field. So this worked, and it was later confirmed by Weier as well. We have already talked about these metal petrol instability in aluminum reduction cells, and that Seele is not sufficient, and that Gerrit did very good work on the coupling of the two interfaces. So he found, by applying theory, potential theory first, that it's very important to look on the ratio of the density jumps at the interfaces between anode and electrode and electrolyte and cathode. This determines the regime. There are 2 different regimes, or 3. So there is a strongly coupled regime for density jump ratios around 1. There's a weakly coupled regime between, say, 2 and 10, and mirrored around 1, and then uncoupled for much higher density ratios or much lower density ratios. And depending on the regime you are in, you either have in-phase fast moving waves, or you have anti-phase slow moving waves. And this kind of wave is much nicer, so it take away our German angst of short circuits, because if both interfaces remain parallel, there will not be a short circuit. So we saw this is a kind of wave we could afford. And theory is very nice. Experiments are nice as well. So what Garrett did after making the theory, he was aiming for experiments, but experiments in real cell are really hard. So he did what we do for most of the experiments we do. We go away from the liquid metal and then try to find a replacement. And there was a suggestion a few years ago by Brandl in Göttingen. It was after 1945, he ran out of money dramatically, and he resorted to bicycle shops for his experiment. Meanwhile, you can buy these things for a few thousand euros. So what we are looking at is an orbital shaker, and we are replacing the self-induced rotating Lorentz force by a rotating centrifugal force provided by this orbital shaker. And what comes out is, for a high density jump at the upper interface, it's between air and paraffin oil, and a low density jump between, at the lower interface, you have this obviously antiphase waves. If the jumps are very similar, the waves are in phase. So this was a nice confirmation of the theory. Then Norbert and Gerrit came up with this table. They found out that we have so many liquid metal battery systems that we can find all regimes there that we can dream of. And there is one special liquid metal battery that's not really a liquid metal battery, but it's an aluminum refinement cell. And this aluminum refinement cell has almost density jump ratio of 1. Interestingly, already in 1925, it was observed by Frary that they have to take care in aluminum refinement to have a thick enough electrolyte layer in order not to have backmixing of the refined aluminum into the scrap metal rich one. So these are aluminum refinement cells, and for me, they have a very positive message, because it took quite some time to develop them. It was started by Hoops in 1901, and first successful cells went into operation in the 1930s, maybe. And now they are working. These are large cells, 3-layer cells, and they provide a voltage, because you have impure aluminum alloyed with copper on the bottom. You alloy it with copper in order to have this stable density stratification, but only the pure aluminum is allowed to pass through the electrolyte and is then deposited on top as relatively pure aluminum that can be used for many purposes. It's better than what comes out of Hall-Héroult cells. It's more pure. But so you have a concentration difference between the aluminum here, the pure aluminum, and the aluminum copper alloy. Unfortunately, the voltage differences that we get are at maximum 40 millivolts. This is not too much, and you have to observe that the electrolyte thickness, for the reasons I just mentioned, is huge. So you will not draw much current. This is not the purpose of the cells, but these are cells that operate at very high temperature, and they are in industrial use for almost 100 years. So this gives me hope that we might see larger liquid metal batteries in future, maybe. yeah, these spiral waves, just very shortly, they are an artifact of high damping. So there is a phase lag, between the wave motion and the orbital motion. And if you have friction, the friction term is from Weier again. If you have friction, then the phase lag depends on the radius. So you have a radially depending friction, and this leads to spiral pattern formation. Was found again first in the theory by Gerrit. We did then an experiment based on background-oriented Schlieren. So what I can show you here is on the left-hand side, the view from the top on these spirals theoretically computed, and on the right-hand side measured. And for us, it looks quite convincing that again, the theory seems to be correct. When Sabrina was with us, we thought about how impurities behave in liquid metal batteries. So we observed in the experiment that we have kind of droplets sticking to the lower part of the anode, or if we have a full drop of lithium or sodium as the anode, then sometimes they do not coagulate anymore, but they simply stay as single droplets with probably some electrical contact. But in the end, we have a situation where there are metal droplets in the electrolyte. And we were curious how they behave, because we observed very rapid decays of the cell voltage. And Norbert thought this might be due to these droplets moving from the anode directly to the cathode, thereby increasing the concentration dramatically. So Sabrina did some computations, again using open foam. We simulated a half sphere that concentrates the current. This concentrated current leads to Lorentz forces from both sides that try to shear the droplet from the anode. In contrast to electroslag remelting and vacuum arc remelting, the net force, so buoyancy, acts upwards. In vacuum arc remelting and electroslag remelting, the heavy metal likes to drop down. Here it likes to come back. So to shear the droplets, you need probably more Lorentz force than you would need in electroslag or vacuum arc remelting. So what we found is that for current densities that are possible in liquid metal battery cells, we could find these droplet detachments, but we could also find situations where we have a almost stationary droplet resting on the anode and not moving away. And when thinking about these droplets, it became apparent to us that we might have not, as so many times before, we might not have fully captured the whole picture, but that there is probably something probably important still missing in the calculations. And this is the topic with which I want to end my talk, and where I promised you at the beginning that I can show you only some phenomena and I'm unable to explain them, unfortunately. So in the next movie, what you will see is this cell. The camera looks from the top, and we have two different kind of particles. There are salt crystals that float on top of the electrolyte. They are white, and they are mirrored on the cathode surface. Yeah, it's pure metal. It's a very good mirror. So whenever you see a salt crystal, you see its mirror image as well. So this is very easy to detect. It's on top of the electrolyte. Whereas there are oxide particles, and these oxide particles, they sit on top of the cathode surface, and they are not mirrored. So what we see here is the oxides stick to the middle, and the salt particles, they move inward, outward, probably driven by thermal Maragoni convection. And now what we did, or what Steffen Landgraf did, he switched. We are back to charge. So the cell is charging at the moment, and the oxide particles, they collect below the anode. And then Steffen switches from charging to discharging now, and immediately these oxide particles, they move from the center of the cell to the rim of the cell. And this is certainly intriguing. So the voltage, or we changed the voltage by about 0.9 volts during this switching from charge to discharge. Again, fear of hate, corrosive environments, and so it drove us to doing substitute experiments with aqueous electrolytes. It's probably a different story, but nevertheless, what we have here is a gallium pool, molten electrolyte containing tin and solid tin anode on top. So we are depositing tin out of the aqueous solution on top of the gallium. And what we do in the movie here is we do nothing, and then we switch on the voltage of a bit more than 1 volt. And what you can see immediately is there is a reaction of the interface shape. So it switches from the blue shape to the orange shape. And at the same time, a very strong flow is generated, and it comes out of the edges here, basically. So we guess that these are related phenomena. And of course, people thought about these things and saw these things years ago. These are drawings from von Stackelberg et al. They were not the first. Frumkin has seen these things. So electrocapillary phenomena are well known. They are probably understood by a lot of people, but not by us, not yet. I hope we are able to improve. The basic idea is the Lippmann equation from 1873 tells you that the interfacial tension, is also shown here, depends on the charge that you have at the double layer. So this is a sketch from von Stackelberg of the double layer. As soon as you have a charge distribution, either way, negative, positive, or positive, negative, along the interface on both sides, you will decrease interfacial tension. Only if the interface is uncharged, it will have its maximum value, the interface tension. So by this way, should you have a potential gradient along the interface, you would drive, depending on where you are on this graph, you would drive a flow inwards or outwards. This could explain something, but it's not the only effect. You have thermocapillarity, solutocapillarity, and the mentioned electrocapillary effects. You can compute, as Garrett did, corresponding Maragoni numbers for this. Turns out that electrocapillarity seems to be strongest. For our LMB observations, we have the problem that we just do not know where we are with the potential, so we do not know on which branch of the interfacial tension curve we are. And solutal Maragoni convection could explain this behavior as well, because the interfacial tension of lithium is lower than the interfacial tension of bismuth. So if you switch from charging, where you remove lithium, to discharge, you add more lithium in the center compared to the rim. So there would be a solute-driven Maragoni convection as well from the center to the rim. In the aqueous electrolyte, the situation is different. There, the interfacial tension of tin is lower than the interfacial tension of gallium, and it would not explain the outwards-inwards flow that we observed. So we think that at least there, electrocapillary effects are likely the reason for the observed flow. I skip the conclusions and go straight to thank you for your extension, and thanks a lot for the members of the team.
Okay, so we have time for questions. Any questions from the floor? Ah, Doug.
Thanks for a nice talk and lots of interesting results. I was really curious about the solutal convection stuff you showed early on, and I guess I have two questions about that. One was you showed where you get this sort of ongoing oscillation. I wonder what sets the time scale of that. And then my other question was you showed these three-dimensional simulations where you've got convection cells. What sets the length scales there?
Yeah, good question for the time scale. Let me have a look.
Yes,
so
it is.
10 seconds, roughly. So the length scale.
But where do you think the 10 seconds comes from? Why is it 10 seconds and not?
I think it should then be geometry, right? So you have this convective time that you need to travel through the cell, and probably I haven't done the computation, so I'm not brave enough to do it now, but I would guess that it should fit.
Okay, fair enough.
And for the size, spontaneously, I think. The initial size should
you have these
be
beautiful structures. I wonder.
I mean, it should come out of the instability, right? So out of the linear instability of these things, that's the most amplified wavelengths that determines the size of the plumes, of the initial plumes. But these initial plumes, they vanish very, very fast when they hit the bottom, and then large-scale solutal flow sets in.
Thanks.
I've got a question myself, actually, which is, in your convection work, you ignore J cross B consistently,
Yes.
and yes, when you're talking about electro vortices, J cross B is actually fundamental. So
Right.
it's clearly the correct thing to do.
When we did electro-vortex flow, we did not ignore J cross B.
Sure.
I haven't carefully enough explained these things.
Yeah.
Of course, it's a vital ingredient. Otherwise, we wouldn't have the flow.
Sure, but you ignore it in the convection calculations.
In the convection, when I talk about thermal convection or solutal convection, I did ignore it completely because the total currents are relatively small. If you do an estimate, we would not expect to have very large electrovortex flows there.
Right, yeah, okay, thank you. Any further questions? Right, okay, thank you. In that case, I think we can proceed to the next talk.